So now here the problem is like we use the sine and cos based periodic functions as a positional embedding to change the actual embedding of the word. And this is the actual problem here, because when we use such kind of encoding and when we change the word's actual embedding, then after a certain limits, it is very tough to extrapolate this. So in that case, some papers actually solve this problem by using the attention with linear biases. Means they remove this positional embedding related attention. They remove all those attentions. Just by we will use that embeddings. For each of the embedding, we will use that all embedding. Suppose our embedding dimension is 4. So in that case, we will just use the embedding. We will not use this positional and some everything. So we will use that just like a embedding. So now how it will change everything. So in that case, our embedding, we will use same process. Like we will use the query and key, then compute the similarity score, then we can just divide by scalar and scale it and get some normalized similarity score between each of those words, but without positional embedding. So suppose now here our 0.8, 0.9, 0.9, 0.9. So this is like that. So this is our new data. So in that case, now how to recover the loss that we have due to the positional embedding? Because if we don't have positional embedding, the hello, if it comes at 0th position and in the same text or sentences or longer sequences it comes at some other position, it will have same effect in the entire sequences. Means it will be tough to differentiate between. So in that case, they prepare the same dimensionality matrices that we have for query and key. So here we have embedding dimension 4. So we have a 4 by 4 matrix. So we will calculate the 4 by 4 matrix. Now, for each of those matrices, we will calculate the bias introduced by this paper. So bias introduced for a position I and j. So for example, I represents the columns positions, I1, 2, 0, 1, 2, 3, 4, j represents the row position. So if a particular data, suppose it is at I1 and J3, I1 and J3, so at this position. So what will be the inductive bias? So what will be the bias, linear bias? Can be calculated by this algorithm. So this algorithm just like a slope into absolute value of I minus j, means just and plus intercept. So suppose here intercept is just 0.2 and slope is minus 0.5. So here slope is actually a learned parameter that controls how the attention bias changes between two tokens, indicating their distance in the sequences. And similarly intercepts, so this is the intercept, this is another learned parameter used to adjust the overall level of the bias. And M is the head specific scalar, because we in the transformer we use the multi-head attention. So for example D13, we can easily calculate, it will be minus 0.8. So now after that our revised softmax can be calculated like that. I am just giving for this two part, not considering the entire, just for simplicity. So this value will be here like 0.5. Suppose we got after entire scaling and everything, so 0.5, and here it will be like minus 0.8, because this is minus sign. So once we calculate the value, it will add some relative bias in this number. Like hello, if hello is distant, hello, suppose how and you both are highly, means they are like, so here you can see that it is minus 0.3. So you can see that some negative biases it is adding in this. So in that case, instead of positional or fixed kind of biases, it is adding some relative kind of things. Like it is not changing the actual embedding value, but adding some linear biases, and which shows that how different both are, what is the difference between them, and which is calculated by using this scheme. Now another thing is like when we use the traditional transformer based architecture and when we calculate the self-attention. So after that calculating the self-attention, we just concate. Suppose we have 8 heads, we just concate all the attention heads value. But here it is different. We add some another bias related to attention heads also. So now suppose we have 8 head attentions, 8 heads for the attention mechanism. It added that value of m, like 1 by, for first head it will be like that, for second head it will be 2 to the power 2, for third head it will be 2 to the power 3, and like 1 divided by 2 to the power 8. Now suppose we have number of heads equal to 16. So in that case we just start with 0.5, then we increase like 1.0, then we say that 2 to the power 1.5, and that same range we can just enhance the ranges for 16 heads. So in that case, suppose then we will use this value as a value of m to multiply with this matrix, and then this multiplied matrix will be added with this here if we have multi-head attention, and then after that it will calculate the softness score, and then we will use the math multiplication and etc. So in that case you have seen that they have made the entire changes at a very low level. Means when we use the transformer, we apply some embedding plus positional encoding, then pass it to attention layer. So at the same area they have made the attack. They have attacked and apply remove the positional embedding through some linear biases to achieve, according to the paper, they have achieved a very good results, and not only like extrapolations, like increasing the size during the text with respect to the sequence length that is used in the training. They have also reduced the time and memory consumptions during the entire training. So I think now it is easy to understand that how such kind of systems are working. So most of the paper which means attack the transformer to solve this problem actually concentrates on this area only, like from starting to attention layer. So thanks for watching.